So now we understand that not only electrons, but also nuclei behave like small spinning magnets. Small spinning charges. It's not correct to say they're rotating charges, but they behave analogously as if they were small spinning electrically charged particles. And like any spinning electric charge, a spinning electric charge generates a magnetic dipole. So both electrons, and in particular for our point of view, nuclei, have a magnetic dipole, which turns out to be an important property of nuclei that we can use to do some chemistry with. So just like any magnet, that magnetic dipole of the nucleus has a particular strength. So we say the strength of that magnetic dipole is this variable we call mu. We can represent that as a dipole moment pointing to some direction in space, just like a bar magnet that can be pointing upwards or downwards, and it generates a magnetic field around it corresponding to what direction it's pointing, and in proportion to how strong that magnet is, the nuclei also generates a magnetic field with some particular strength, and that it points in some particular direction. And the reason that's relevant is because the energy of the nuclei in a magnetic field can be determined by this expression that the energy is negative the magnetic dipole moment multiplied by the magnetic field strength. So if we have a nucleus, if we, let's say, have some nucleus with some particular magnetic dipole, and if we place a larger magnet nearby so that this nucleus experiences a magnetic field, then the energy of this nucleus in that magnetic field is given by this expression, and the spin quantum number tells us the allowable values of these, the magnetic dipole. So what that means is if we were to draw an energy diagram for a spin 1/2 nucleus that can have two values of the spin up or spin down, the values of the spin can be minus magnetic dipole times the magnetic field strength, or plus magnetic dipole times the field strength. When the magnet is aligned with the the magnetic field, the energy is lower because of this negative sign. When it's opposed, spin down, opposing the magnetic field, then the energy is higher. And the difference between those two is twice the magnetic dipole times the field strength. So that difference in energy between the two different spin states of the nucleus turns out to have some important consequences. I will say that for every different nucleus, the magnetic dipole has a different value, different strength. So a proton's magnetic dipole is different in strength than a lithium atom's magnetic dipole, and so on. Protons are one of the most important quantities that we evaluate the magnetic dipole of. So this magnetic dipole moment for a proton for the nucleus of a hydrogen atom is 1.4 times 10 to the minus 26th joules for every Tesla. And Tesla is a unit of magnetic field strength. So just to give you some idea of how strong a Tesla is, and Tesla not the car, but again the magnetic field strength, we know that the Earth has a magnetic field. That's what makes compasses work, right? There's a relatively weak magnetic field at most places on the Earth. That in units of Tesla, the Earth's magnetic field is about 5 times 10 to the minus 5th Tesla. So Tesla, 1 Tesla is a relatively strong magnetic field. A relatively weak magnet, like a refrigerator magnet, strong enough to stick to a large piece of iron like your refrigerator. A refrigerator magnet is about 100 times stronger than the Earth's magnetic field, so that is about 0.005 Tesla is the strength of the magnetic field generated by a refrigerator magnet. A much stronger magnet, these days you can get relatively cheap neodymium iron boron magnets, consumer grade magnets that are quite strong. Those are typically about 1 Tesla or a little bit larger. So those are quite strong magnets. So that's the general size of a Tesla. And then it gets progressively more and more difficult to make the magnets stronger. Not an electrodynamic magnet, but if you have a magnet with a fixed magnetic dipole, that turns out to be the strongest ones that have been made so far these days are about 45 Tesla or so. So about the strongest magnet we can make is only 45 Tesla. So that's just to give you an idea of the size of this unit of a Tesla. And that's the splitting in energy between the lower and the upper states for a proton, depending on whether it's pointing spin up or spin down, is given by this magnetic dipole multiplied by the magnetic field strength with this factor of 2. So as an example of how that works out, let's work this example. Let's say we have a proton in Earth's magnetic field, like almost every proton in any compound that we would make in the laboratory. All those protons are experiencing a magnetic field of about 5 times 10 to the minus 5 Tesla. So what that means is there's going to be slightly more of them in the ground state than in the excited state. So let's see if we can figure out how large that excess is. How many more of them are occupying the ground state than the excited state at a temperature of 300 Kelvin. So the first thing we can do is to say this splitting in the energies between the two states for these protons. The magnetic dipole strength is 10 to the minus 26 joules per Tesla times 1.4. The magnetic field strength is 5 times 10 to the minus 5 Tesla for the Earth's magnetic field. So this number works out to be 1.4 times 10 to the minus 30 joule. That's the difference in energy between those two states. If we want to know something about the probability of being in the upper state is e to the minus energy in the upper state over the partition function, which I can write as e to the minus energy in the upper state over kT plus e to the minus energy in the spin up state over kT plus e to the minus energy in the spin down state over kT. So that's how I would calculate the probability in any one of these states. If I rearrange that equation a little bit, on the top and the bottom, if I just divide through by this exponential, e to the minus energy over kT, I'll get a 1 in the numerator, a 1 for this first term in the denominator, which looks the same, and then the next term in the denominator is going to be e to the minus energy of the spin down state minus e to the minus energy of the spin up state. So e to the minus difference in energy over kT. So that's the delta E that I've just calculated here. kT if we're at a temperature of 300 Kelvin, then if I multiply that by Boltzmann's constant, it turns out that kT is about 4 times 10 to the minus 21 joules. So notice there's 9 orders of magnitude difference between this difference in energy of these two nuclear spin states and kT. kT is much, much larger, 10 to the 9th times larger than the difference between these spin states. So the very little difference in energy at 300 Kelvin between those states. So if I plug the numbers into this expression, 1 over 1 plus e to the minus this ratio delta E over kT, so 10 to the minus 30th divided by 10 to the minus 21st. That ratio worked out to be 3.4 times 10 to the minus 10. So we can, even before we plug this into the calculator, we can see roughly what's going to happen here. E to this very small negative number is a number very close to 1, just a hair smaller than 1, e to the minus very small number. So I've got 1 divided by 1.9999999. So it's almost a half, but it's a little bit larger than a half. And when I do the calculation exactly with the proper number of sig figs, again, the sig figs in this exponential, the 1 sig fig in the exponent turns into a number that's differs from 1 by a number very far out past the decimal point. So it's 0.9999999, and about 10 decimal points later is the first non-9 digit, and that's the first significant digit that we keep. So what that means is when we compute this with the correct number of sig figs, the fraction of nuclei, proton nuclei that are in the spin up state, which is slightly lower in energy than the spin down state, is not exactly 50%, but is 0.5 followed by 9 zeros, and then eventually we see an 8. So 0.5000008 of the nuclei are in the spin up state, and 0.499999992 of the nuclei are in the spin down state opposed to the electric field. So certainly this is very close to 1/2. The excess of nuclei in the spin up state is close to 1/2, but not exactly 1/2. There's a very slight excess of protons in the spin up state. You might think that this small excess in this relatively weak magnetic field would be not terribly consequential, but it turns out that in this magnetic field strength, or particularly in stronger magnetic field strengths, that excess is something that we can make a lot of use out of as chemists. So that's what we'll talk about next.